In this video, we'll introduce the ARIMA models for time series analysis. Specifically, we'll give a brief history of ARIMA models and then introduce all the models specified here: Autoregressive models, moving average models, ARMA, ARIMA, SARIMA, and ARMAX. In the next videos, we'll explore these models a bit more, learn how to identify which models our data seems to come from, estimate the model parameters, and diagnose our model for any problems. The sources of ideas are hard to pinpoint and are often shared across many people. Still, the main contributors I could identify are the following. In 1927, a British statistician by the name of Yule published the first paper on autoregressive models, addressing the problems of sunspot periodicity. Before Yule, scientists predominantly attempted to model these cycles as deterministic. Yule introduced a statistical approach utilizing an autoregressive model of order 2 and demonstrated that this method could produce quasi-periodic behavior where cycles are not fixed but fluctuate within a range, providing an excellent fit to the observed data. Walker, a Cambridge mathematician, grew increasingly concerned with global weather patterns. He extended Yule's work by developing autoregressive models of order P and applied these models to analyze air pressure data relating to the Southern Oscillation. About the same time, a Soviet statistician and econometrician named Slutsky discovered that summing or averaging random variables over time can create series that mimic real-world phenomena like economic cycles. In this graph from his paper, you can see both the real data of English business cycle and data generated from a model of summing 10 random numbers together. This gave birth to the moving average processes. In 1938, the first comprehensive book on time series analysis was published by the Swedish statistician Hermann Wald. Wald combined autoregression and moving averages into a single process called ARMA. The most widely used book today, however, is Time Series Analysis, Forecasting and Control, first published by Box and Jenkins in 1970. They developed the ARIMA models and also standardized the iterative cycle of specifying a model, estimating it, diagnosing it, and repeating until a suitable model is found. Numerous other authors made significant contribution to the field of time series analysis over the years, some more practical, some more theoretical. I list here some of the names I encountered when preparing this video. Autoregressive or AR models are built on the assumption that the value of a current observation is primarily determined by its past values, plus some new random shock or noise. This assumption allows AR models to capture the dynamics of systems where the present state is influenced by previous states. Some examples of AR models in practice are temperature. The temperature on a given day can often be predicted based on the temperature of the preceding days, plus some random fluctuations due to external factors. Economical variables such as interest rates, GDP, or unemployment rates are often autoregressive, where the current value is a function of its previous values plus some new change. Reservoir levels are another example, and physical systems is another. For instance, the location of an object in space is determined by its previous position and velocity plus any new force or movement applied. And AR models are particularly useful in modeling processes with long-term dependencies, where past values have a lasting effect on future outcomes. An AR1 first-order AR process can be written like this. The current value, x of t, depends on some linear function of the previous value, x of t minus 1, plus some new shock, epsilon t. The epsilons are considered IID from some distribution, for example, normal with a mean of 0 and constant variance. We can easily incorporate a constant mean, but this usually isn't very interesting as we can simply model the d-mean series x minus mu. An AR of order p is one where we use the p last observations as shown here. Moving average models assume that the current observation in a time series is a linear combination of past random shocks and a new random shock. These models are useful for capturing short-term dependencies where the influence of past events diminishes quickly. Examples of MA models in practice include sales. For example, the impact of a holiday sales may linger for a short period after the holiday has passed, affecting sales numbers for a few days or weeks before normalizing. Server load. After a surge in traffic, for example due to a major event, Server load may remain elevated for a short time as users continue to interact with the systems, but eventually it will return to its typical levels. MA models are particularly suited for scenarios where the effects of shocks die out quickly, making them ideal for modeling short-term dependencies and transient effects in time series data. An MA1 is written like this. The current value x of t is equal to some new shock epsilon t plus a lingering effect from the previous shock epsilon t minus 1. An MA of order q is simply a model where we use the previous q shocks as shown here. Again, we can also incorporate a constant mean, but we could also look at the time series after we removed it. The name average is a bit misleading as the thetas don't sum up to 1 and can even be negative. ARMA models are simply the combination of both these models. We assume the current observation has both long-lasting dependencies captured by the previous value and short-term effects captured by the previous shocks. An ARMA 1.1 is a model where the current value x of t depends on some linear function of the previous value x of t minus 1 plus a linear function of the previous shock plus some new shock. The ARMA PQ is simply extending this to using p past values and q past shocks. Notice that the model has in total p plus q plus 2 parameters, since we also need to estimate the mean and the variance. And it turns out that many world phenomena can be adequately modeled by these models, usually with order of not more than 2. The primary focus in ARMA models are time series that display some statistical equilibrium, which is called stationarity. We will learn more about it in the next video. But sometimes we have non-stationary data that still displays some form of homogeneity. That is, the series' local behavior is similar between different parts of the series. Or the local behavior of the series appears to be independent of its level or slope. In this graph taken from the Box and Jenkins book, the upper part shows a series that display different levels in different times, but if we zoom in on the local parts, the series seems similar. The lower part shows a series with different levels and different slopes, but again, zooming in, the local parts seem similar. These differences can be eliminated if we take the difference between time steps. The first difference will eliminate the level, and the second difference will eliminate the slope. ARIMA stands for Autoregressive Integrated Moving Average, and the idea is that after differencing, we have a stationary process, and we can perform ARMA modeling on it. The first order difference is defined simply as the current observation minus the previous one, denoted by ZT of order 1. We can also have D levels of differencing, that is, differencing the different series up to some order. ARIMA PDQ is doing ARMA PQ on the D times difference series, and we can write it down in mathematical notation. The term integrated is used because we don't care about the difference of xt, but of xt itself, so we need to sum up those differences to get back the values we are interested in. Certain time series data exhibit clear and predictable seasonal patterns, where observations repeat at regular intervals, known as seasons. Here's an example of such a time series where you can see a clear seasonal pattern. Modeling these patterns are crucial for accurate forecasting and analysis. Examples of seasonal patterns include electricity consumption. Power usage typically peaks during the day but drops at night. Retail sales. Sales often peak on weekends as more people shop on Saturdays and Sundays. YouTube traffic. Views for educational videos might be higher on weekdays and lower on weekends. Credit card spending may show monthly cycles, and tourism activity or influenza cases may show yearly cycles. To model these patterns, we define the number of seasons that complete a cycle and denote it by C. The value of C depends on the context. C can be 24 hours per day, 7 days per week, 30 days or 4 weeks per month, 52 weeks, 12 months, or 4 seasons per year, etc. The notation for SARIMA model is to add another parenthesis for the seasonal components. The lowercase p, d, and q refers to the regular ARIMA, the uppercase refers to the seasonal ARIMA. For example, if the cycle is 12 steps, then seasonal AR1 is this, and seasonal MA1 is this. This is a SARIMA model with a non-seasonal autoregressive component of order 1 and a seasonal autoregressive component of order 1 with a seasonal period of 12. And you can have more and more complex models here. A question left for the viewers is when we have both a regular differencing and a seasonal differencing, which one should be first? Think about it and leave your answer in the comments. What if we want to include exogenous variables to the model? That is, we have a y and we think it's related to some x variable, but in addition it's also related to its past values and some past shocks. This is called ARMAX or ARIMAX, and x stands for exogenous. The simplest way would be to include the covariates in the right-hand side of this ARMA 1,1 equation. The problem is that it makes it difficult to interpret the beta coefficient. For this sound reason, Heinemann, who is a statistics professor from Australia known for his work on forecasting, prefers doing regular regression with ARMA errors. The first line here shows the regular regression, and the second models the eta errors from the regression as an ARMA process. Both approaches perform equally when it comes to forecasting, but the later is easier to interpret. We could also do ARIMAX by differentiating all the variables and doing ARMA on the errors. Well, that's all for this video. See you in the next one.